Hello, everyone. My name is Sadeh Farhad Khani. I'm a PhD student at EPFL, and I'm going to present our work on the strategy-proofness of the geometric median, which is a joint work with El-Mehdi El-Mahamdi, and Rashid Gheraoui, and Len Yung-Hwan. Okay, in this work, we consider vector aggregation as a voting problem, meaning that we assume that there are several users in the system and each user proposes a vector, and the goal is to aggregate these vectors into a single vector, which is the output of the system. So in this example here, the blue dots are the input vectors or the votes from the users, and the golden star is the output vector, which is the result of our voting system. There are many candidates for aggregating several vectors into a single vector, such as the average or the geometric median, which is the one that we consider in this work. And we will see about them more in the next slides. The main application of this vector vote problem is probably collaborative machine learning, in which we may want to aggregate local models from different users, or gradient vectors or preference vectors that are somehow learned for each user. And it actually makes more sense to look at the problem as a voting problem when the model is going to be used for decision making, and it may affect people's life. For instance, consider the case that a machine learning model is used to decide the amount of tax that each person is going to pay. In this case, different people might have different preferences, and it actually makes more sense to look at the problem as a voting problem that is somehow going to capture what the majority of people want, and to somehow simulate digital democracy. As I said, in this paper, we consider one specific aggregation rule, the geometric median, which is a generalization of the median to high dimension. There is actually no closed form formula for the geometric median, and in order to compute it, we need to solve an optimization problem, which you can see here. The geometric median of endpoints θ1 to θn is the point that minimizes the sum of the distances to this point. And yeah, the solution of this optimization problem in one dimension is exactly equal to the median. The geometric median has several nice properties that make it very popular in practice. The first property is that, as opposed to the average, the geometric median is actually robust to the outliers. In this example here, we have several users that agree pretty much on the same vector, but we also have 3 outliers that for some reason disagree with others and propose values that are very different from others. As you can see here, if we use the average, the outliers can actually move the output to the right as much as they want. But this is not the case for the geometric median, and the output of the geometric median remains somehow in the region that the majority of vectors are, no matter how far these outliers go. The second property, which is somehow also connected to robustness, is that the geometric median satisfies a special type of fairness principle, which is one voter, one vote with a unit force. What does it mean? It means that the computation of the geometric median is actually equivalent to the scenario in which each vector pulls the output of the geometric median to itself with a unit force. And the geometric median would be the equilibrium of this process. For instance, in this example here, as we have 3 vectors and each of them has a unit force, there should be a third of a turn between any 2 arrows. And it doesn't actually matter if one of these vectors moves to the right, as the unit force remains the same and in the same direction. So the geometric median doesn't move, and this vector cannot actually obtain more voting power by moving far away from the geometric median. For a detailed discussion about this property and why it's the case, you can check the paper. And because of these nice properties, the geometric median has been used a lot for robust machine learning, for instance, for Byzantine robust optimization. And yeah, the question that we ask in this paper is about another property, which is called strategyproofness. And we are interested to see to what extent the geometric median is actually a strategy proof. What is a strategyproofness? Strategyproofness is a desirable property that ensures that it's in each user's best interest to behave truthfully and to reveal their true preferences. So we consider a strategic user and we assume that this user has a true target vector T. And we also assume that the user behaves strategically, meaning that they may actually report another strategically crafted vector S if it's in their best interest. The goal of the strategic user is then to move the output of the aggregation rule as close as possible to their own target vector T. So if we assume the output of the aggregation rule is the star on the left, in this case, the strategic user is not going to be very happy as the output is actually far away from their true target vector. But if the output moves to the right, as you can see, the strategic user becomes much happier as it's now close to their target vector. Strategyproofness is a very desirable property to have, as if the system is not strategy proof, then the users have actually incentives to lie and misreport their data, and this may compromise the trustworthiness of their data and the collected data set. So ideally, we want the system to be a strategy proof, especially in the cases which users have incentives and personal preferences. But it's also a very difficult property to satisfy and to prove usually in practice. Okay, as an example, a well-known result is that averaging is not actually a strategy proof, and the strategic user actually has a full control over the output of the average. In this example here, assume we have 2 honest users that report 1 and 2, and the target vector of the strategic user is 3. Now, if the strategic user behaves honestly and reports 3, the output of the average is going to be 2, which is not ideal for the strategic user because there is a distance between the output and their target vector. But if the strategic user lies and reports 6 instead of 3, the output of the average will be exactly equal to 3, which is exactly the target value of the strategic user. Therefore, the strategic user can actually gain by lying and misreporting their value, which means that averaging is not a strategy proof mechanism. There is also another well-known result in 1 dimension by Mullin, who proves that the median is actually a strategy proof in 1 dimension. The proof is quite simple. In the previous example that we had, as you can see, if we use the median, the strategic user can choose a point between 1 and can choose actually any point between 1 and 2 for the median. And the closest point to their target value is 2, which is already achieved if the strategic user reports its true target value 3. So it's not actually possible to do better than that. So the system is a strategy proof. The case when the number of users is even is a bit trickier and requires some special considerations, but still follows from the same kind of reasoning. And in our work, we try to generalize this result to higher dimensions. For this, first we define what we call the strategic gain, which is the maximum ratio between the distance of the geometric median to the target vector with a truthful report to this distance with a strategic report. Intuitively, we want this strategic gain to be as small as possible, and if it's equal to 0, the system is completely a strategy proof. For instance, it's equal to 0 for the median, which we just saw, and the median is a strategy proof. The first result of our paper is actually a negative result, saying that if the dimension is greater than or equal to 2, the geometric median is not even approximately a strategy proof, meaning that there is no bound on the strategic gain, and it can actually be arbitrarily large. The full proof of this theorem is quite complicated, and you can check it in the paper. But I have a simple example here showing that how it's possible for the strategic user to gain by lying and misreporting their vector. In this example, we have 2 honest users, and user 2 actually reports a vector theta2, which is very far on the right. As you can see in this example, if the strategic user reports vector S, which is a bit higher than their true target vector T, they can actually bring up the geometric median a bit closer to their target vector. And therefore, the strategic user can actually gain by misreporting their vector, which means that the strategic gain is positive and the geometric median is not completely a strategy proof. Yeah, as I said, what we prove in the paper is actually stronger than this, as we show that this strategic gain can actually become arbitrarily large in some corner cases. On the other side, we also have a positive result in the paper saying that under a mild smoothness assumption on the distribution of the vectors, the geometric median is asymptotically approximately a strategy proof. It means that if the number of users is large enough, with high probability, the strategic gain would be bounded by parameter alpha. In the paper, we compute this parameter alpha as a function of the distribution followed by the reported vectors. And intuitively, the value of alpha depends on the degree of skewness in the distribution of the input vectors. So if the distribution is highly skewed, the geometric median becomes less strategy proof. For instance, in this example here, we have 2 different cases. In the case on the left, where the vectors are almost equally distributed in both dimensions, the value of alpha would be small and the system is actually more strategy proof. But in the case on the right, as the vectors are flattened somehow in one dimension and is highly skewed, the value of the alpha is actually large and the system is less strategy proof. And yeah, we also generalized this result in 2 different aspects. One is skewed preferences, which is the case where different dimensions have different values for the users. And the other one is what we call the skewed geometric median, which is a modification of the median that we design in order to improve the strategy proofness of the geometric median. You can check the details about these generalizations and the corresponding results in the paper. And yeah, thank you for your attention.